Hi everyone. So my talk to be on explaining Spack for MPICH's CI suite. So I'm going to introduce myself real quick. So I'm Wong. I'm part of the Argonne's leadership computing facility. So my day job is mostly maintaining the foundational software stacks that you need to run AI ML workloads on Aurora or the other Argonne computing infrastructure. And my co-speaker, which is in the audience right here, is Ken Raffinetti. He's part of MCS, which is what the division I used to be part of, and we are both maintainers of MPICH. So for those who don't know, MPICH is a leading OpenMPI, or sorry, not OpenMPI. It's a leading MPI implementation. So DOE and Argonne invests a significant amount of manpower to develop this, and our hardware vendors as well also spend significant amount of effort to put their contributions into MPICH. And so conversely, it's a very large open source project, and we receive a lot of contributions that we have to work through on a daily basis. But we're a small team, so we really rely a lot on having CI in our developer workflow to optimize away the tedious aspects of maintaining a large project. So the primary benefit of our CI suite that we have is mostly that we have holistic coverage from it. So we test out a multitude of configurations for MPICH through our CI suite. So we'll try out different compilers, we'll try it out on different operating systems. So we'll try like BSD, we'll try out Linux, Mac OS, x86 and ARM, Apple Silicon. We'll try out different configuration options. We'll try debug builds, we'll try address sanitizer builds. We'll try out MPICH has async progress as a feature flag, so we'll try out async progress as a feature flag, and we'll also try out GPU collectives on particular hosts, for example, with NVIDIA GPUs or AMD GPUs or whatnot. So this provides us the harness for having these tests all be done in a relatively automated manner. And in addition to that, all our PRs are tested against our CI infrastructure. So mostly for correctness testing. So prior to anything being merged, runs through our CI suite, make sure that it's validated before everything is merged up to main. And in addition to that, we also have nightly runs against our mainline branch for as a additional check, as one would say. But the mainline nightly runs are much more holistic in that regard. In comparison, the PR tests are much more, how do I put it? Much more focused. So in our nightly jobs, in practice, we have about 300 unique jobs. So those test out every individual permutation of builds that we do. And in practice, that means that we have an explosive amount of combinations that we actually need to test. So in practice, about 1,500 runs is what we run nightly against our mainline code base. So this is what it kind of ends up looking like on our Jenkins CI server. So right here is midnight CST, and our entire CI infrastructure is overloaded at that time. And then throughout the day, it slowly drains down as jobs get finished. So quite intense on our infrastructure. And that's primarily because our CI pipeline is very slow. So on average, each individual run, so out of the 1,500, each one takes about an hour and a half to finish. And so this is a very significant detriment to our performance and for our productivity. So in the event, for example, that we rerun the nightly pipeline during the middle of the day, I may or may not have blocked the CI in the first place, so we can't test our PR runs. So this is not ideal, of course. And I think a very large part of our CI is taking about hour 50 per run is that we rebuild a lot of components of MPICH prior to the actual test suite being ran. So we build every single embedded dependency for MPICH per run, which is fairly wasteful. On top of building MPICH itself with the relevant changes that are being made, we build our entire test suite on top of that, and it links against MPICH before the runs even occur. And so there's a lot of room for optimization in that regard, which is what our work has mostly been done to improve that. And in addition to that, builds are very reliant on our host agents system packages, which isn't ideal as well because we have to, one, maintain consistency on our end as developers to make sure that we are testing against the versions of packages that we are expecting to be running on our production hardware. And it also means that we have significant effort if we want to test any arbitrary versions. So say like we want a new version of libfabric or a new version of UCX, we want to test against an MPICH, we would have to go and install it ourselves manually through opt or whatnot. And that's just effort on our ends that we'd rather not be doing as developers. So fairly inflexible, not ideal. And this job seems awfully appropriate for a package manager, as I would say. My background, actually, I have a pretty significant background in open source. I'm a Nix packages contributor, and so I see a lot of benefits and the parallels that Spack brings to the CI infrastructure or CI ecosystem for HPC. So why Spack, right? I mean, it's pretty good at caching build configurations, I would say. So anything that, or any build that uses the same configuration flags or variants would be cached if it's found in the installation cache already, which means that will save us a significant amount of compilation time in the event that the builds that are generated by our CI suite isn't unique. So in addition to that, right, we have very declarative build and test environments from Spack. Right? We can define a YAML file, and that can pull in the version of MPICH that we want with all the versions of libfabric and UCX, for example, that we want, which is really convenient for both a CI environment where we want to make sure that the exact dependencies that we're trying to build against and test against are in the environment at runtime. But also, it's useful for us as maintainers, so if we want to replicate that exact CI environment from our build system on our local machines, for example, or on a shared machine that we already have access to. So pretty great benefits, I would say, that in theory. And on top of that, HPC is a first-class citizen with Spack. Our CI infrastructure at the lab is primarily shared multi-user machines, traditional Linux installed with NFS shares that are pinging between the devices to react as a shared file system. Spack integrates pretty much perfectly with that. And in addition, Spack is also used a lot by our end users at the lab, meaning that we want to test out this deployment method in our own CI suite. So that's the theory. So in practice, how should we do this, right? It's our existing CI setup is primarily a bunch of hand-rolled shell scripts over the years. They predate my existence in this world, to be genuinely honest. So a lot of it is hand-rolled shell scripts, Perl scripts, Python scripts that were built up over the span of 2 decades to test out the various facets of MPICH against our own hardware, right? So in practice, that means we really want to minimize the amount of changes we make to our CI script setup, which really means that we can probably get away with only substituting out compilation with Spack. And ideally, right, we only really want compilation to be done and environment loads to be handled by Spack, and then everything else can be done with our existing harnesses that we've developed over the years. So that's the idea, right? So let's try that out. Yeah. So we have a general design, right? We can take each MPICH component and kind of treat it as a Spack package, right? So this is the MPICH dependency tree right here. So the low-hanging fruit, I would say, for these dependencies would be like hardware lock, libfabric, UCX, and Yaxa. These are all existing options in our automake configure scripts. So these are pretty easy to factor out and just treat them as if they were an embedded shared library on the system, and which Spack handles pretty well. But the less easy to do ones would be, say, JSON-C, for example, which doesn't exactly have a configure option available in MPICH currently, or like our test suite, for example, which is in tree, and it's more or less tied to the installation of MPICH itself. So those are a little bit harder, and same thing with MPL and Romeo, because these are also in-tree dependencies that which their entire source lives within a subdirectory of MPICH. So those are a little harder to factor out, but I would say the low-hanging fruit of these libfabric, UCX, and these other large system libraries that we could use were the easiest ones to start with. So our idea was that we could take these components, right, make individual packages for each one, right, and actually, in fact, most of them are already prepackaged by Spack in Spack packages. So we could take the upstream package definitions, and we can more or less soft fork them, or we can inherit them as like a child class, and that allows us to have some direct control over MPICH's dependencies. So for example, for libfabric and for UCX, we have our own forks on our own GitHubs, so we can add a version tag, for example, with the commit SHA that we want, and with a semvar tag and whatever that we need, so we can reference this in our build scripts, which is very useful. And it also lets us do other special things like run an autogen, for example, if we're building from source or directly from Git, which is super convenient for our own use and lets us be flexible with our approach of building MPICH dependencies in our CI, even with Spack being embedded into our pipeline. So this is kind of what our internal Spack repository ends up looking like. So we have this on our NFS share, and each individual package essentially has its own package definition, and that's either a soft fork from upstream, or we overwrite it and build our own. For example, like for the actual MPICH package, we want some more granularity and control, so we don't use the upstream one, for example. But all that is handled by Spack, so it's a very intuitive workflow in that aspect. So we kind of then moved on from, okay, so we have these components separated out into different Spack packages, right? How do we correspond our Jenkins runs to the corresponding build targets and spec variant definitions? That's not exactly too obvious. So in our existing CI, we have labels that correspond to sets of configure options that we want on our individual build jobs. So for example, this is a MPICH, the OSX CI job. So we have a configuration matrix here to test out a few of netmods and devices. So we have 2 configurations with the CH3 device, and 1 with the TCP netmod, 1 with the socket netmod, and then we have 1 with CH4 on OFI, for example. And then we also have another label for the compiler, so we can choose between GCC and Clang, which we want to test against. So in total, that's about 6 jobs, right? How do we translate that to Spack environments? It's not too obvious. Well, we can generate equivalent Spack specs, if you think about it, with these labels. So we already have a mapping between the labels and the configure options just from our existing test suite harness, which is convenient. So we can reuse that, and if we treat the individual Spack variants as a configure option from automake, for example, we can kind of do more or less a one-to-one mapping between the configure option to a Spack variant, and then that allows us to, at the Spack level, define which configure options correspond to which Spack package we want pulled in at test time. And so alongside that, we can also explicitly define dependencies, for example. So like libfabric UCX, for example, if we want to use particular versions on top of selecting the particular device and netmod, we can do that. And so here's an example of what we have right here, right? So this is a pretty typical CH4 OFI MPICH build. So we're building with the device specified without XPmem. We're using RPath for our wrapper dynamic link type, and then we have the embedded version of hardware lock and the embedded version of libfabric, right? So we can convert this pretty much one-to-one, right, to a Spack spec that has the equivalent values present. And so it's almost, it follows a very consistent pattern as well. Like, so apart from like having these with device being separated out into 2 Spack variants, we have the XPmem one end up being a binary feature flag. We have wrapper DL type end up being a multi-option variant. We have hardware lock as a binary variant as well, and then we also have the explicit dependency declarations as well. So this works out pretty well, and I think you can envision that you could generalize this to a script that, with some opinionated behavior, will template out Spack specs and environments from the configure options that we would have passed as ourselves anyways. And in addition, that allows us as maintainers to use this, this script to also just translate our configure options that we would have passed ourselves anyways when doing a local build to the equivalent Spack package, equivalent Spack variant, and then that allows us to use that spec to pull in the pre-cached build from our CI infrastructure, which is really convenient. And in addition to that, we have our PR jobs, for example. We need to pull in particular SHA-Git revisions from our Git repo. So we can either use, there's kind of two approaches. You can either use Spack develop, and then use the local path option to emulate as if you were pulling from a local source build and then building that, which still allows you to cache the corresponding install, which is super powerful. Or I've noticed through playing around that you could use the SHA-1 git tag even if it's from a fork or from not directly the parent repository, which is super convenient as well. So in practice, that means that we have PR job set up. So if we run our test trigger, we can get a CH4 or UCX run automated, and that's with Spack building it, which is great. And an interesting consequence about all of this is that when we were integrating Spack into our CI infrastructure, that Spack installs were actually ran in parallel per job. So you can kind of envision that each build agent had a certain number of slots available to build a job, right? So each agent had, say, like 4 jobs available, right, 4 slots. And so in practice, that means that if we build multiple jobs concurrently, each one gets picked up by an individual agent. And they kind of, especially if the builds have dependencies that aren't pre-cached yet, they'll be cooperatively built at the same time. So for example, I have an example here where there's 3 separate jobs, completely different versions of MPICH with different configure flags being built, but the common ground is that all of them rely on having an embedded version of hardware lock, all of them rely on having an embedded version of UCX or libfabric, depending on which option that was selected, or all of them require a version of JSON-C, for example. And all these would end up getting figured out more or less by Spack and built over the span of maybe like 30 or 40 so minutes in comparison to each individual run spending the equivalent time building it themselves, and then also having to redo it every single time because they're not cached afterwards by Spack. We did actually run into a bug while doing this, though, and this was a known issue already on Spack's GitHub, but there was a very particular condition where the build installation would exit early because it would detect another process of Spack installing packages at the same time as the other, but it would detect that and then exit the loop and then quit out, thinking that it's done when it wasn't. So thankfully that with my debugging and a bit of probing Todd on the Spack Slack, we were able to get it fixed out really quickly. So very thankful to you, Todd. I was banging my head on my desk for a few days trying to figure out what the hell was wrong with Spack, or if it was just me, or if my CI scripts were broken or whatever. So really appreciate it. Yeah. But yeah, so it was really interesting. And in practice, it also means now that we have really nice speed up in our CI suite. So on average, it's about 33% of increased improvement. And if you notice, even our Spackified runs here, even if they're initially ran while any dependencies pre-cached, meaning that all dependencies of MPICH are built from source, we already see about like a 20% improvement, and that's largely due to the builds of dependencies being cooperatively done rather than being rebuilt individually per run. And then once those dependencies are actually additionally cached on top of that, we see like a sub-hour runtime. And at this point, we can attribute a large amount of that total job runtime to be our single-threaded test suite, which takes on average about like 40 or so minutes to run. And on top of that, our compilation of our test suite, which hasn't been factored out to be aggressively cached by Spack yet, being about like 10 minutes or so. So the bottleneck is very much not MPICH compilation anymore, unlike what it used to be. So big improvement overall, big win. Say. And we also benefit from huge quality of life boosts, which is really nice. So we have any MPICH install that's built from our CI. It's in a common Spack install cache that we can pull from now as maintainers, which means we can avoid doing rebuilds on what our CI has already done for us. We have a more or less clean room environment for our CI jobs, since Spack handles every single dependency. It also means our tool chain is handled by Spack as well, which means that we don't have to worry about what's necessarily on our host systems or on our host build agents at build time. We can just trust that Spack will pull in the relevant packages from wherever source, whether we use E4S or if we just source compile everything into our own install cache. We can trust that more or less it's a clean room environment for builds, which is great. Obviously, external dependencies are now built independently of MPICH, which really provides that speed up. And then, yeah, for matrix configurations, the identical configurations are now cached, and that also means that we save a significant amount of runs that would have been done excessively, which is great. And so we see really big potential in integrating Spack for our CI use. I think this really parallels what people are doing in industry, adopting Nix and other UV and other similar package managers that provide all this aggressive caching functionality. I think that a very natural progression from where we are currently is to further refactor out these internal modules that we have, so be it MPL, Romeo, whatnot. We can do further work to improve our build system to be able to treat these as embedded shared libraries in the first place. We can precompile our entire test suite. This is a little bit harder because we kind of need to presume that the test suite's compiled but depends on a version of MPICH. So we need some sort of monadic build system, kind of, which I don't think necessarily Spack has yet, but it could be engineered from a lot of hackery and maybe some Squash FS images or something. We also want to try out the Ccache functionality in cache or in Spack, because that can provide greater granularity down to the translation unit instead of per package granularity. So that could be even better speed up, especially for like PR builds, for example, which where very little object files change in practice. And we also can mirror our CI builds for public usage too. So say a user tries a bug fix, for example, or needs to try a bug fix, instead of telling them to --configure, make J whatever, and then they have the wrong environment so that their builds aren't necessarily equivalent to ours, we can just tell them, hey, pull in our Spack environment that we have from our build cache here. It's all on the same machine that you're using as well. And it creates a lot less friction from the user side, which is great. So we can try that out as well. And the idea of exporting our test environment as OCI images is also fairly tempting too, although we don't have as much support for OCI runtimes in our current production hardware. So, but anyway, future bright for our CI, that's the point. And so that's pretty much all I have. That's more or less what I went through. And so I'm really thankful. Thanks, guys. This is my first Linux Foundation-esque talk, and it's actually kind of a dream of mine to give a talk here. So dream come true, per se. If any other project maintainers are here that do HPC-focused work, I think this is a very good case example of trying to integrate modern CI principles into a HPC-focused environment. And so yeah, so thank you so much. Any questions, feel free. I'm happy to answer.
Okay, thank you, Ethan. We have 5 minutes for questions.
So yeah, this has been a great example for me, because I've seen several specific pieces of work that went in for some of the efforts that we did at Sandia for one of our large code suites that I think directly benefited the CI. This is a great example of a smaller microcosm of the kind of breaking a big package down into little pieces and gaining some of the benefits from that. This is a really good example. I think it's more applicable or more easy to realize some of the benefits in MPICH than it is for the physics code that we're applying it to, but it's really good to see that this.
Yeah, and honestly, I also think it really instills good habits as well, because these modules really should be able to be factored out in the first place. So the fact that they're not able to be factored out means that you have some to-do lists to be adding to your issues page.
Totally agree. So my question, though, is from earlier. There was a specific point where you said something about you want to exercise better control over your dependency stack, right? You didn't want to necessarily have to rely on the system package manager provided dependencies.
Absolutely, yes.
So on my other project, we have the same opinion, right? We use Spack to build it as far down as we can. But I do have some heartburn about users may not want to use Spack. They might still want to install MPICH directly against those system-provided dependencies. Do you still test those anywhere in your CI?
Yeah. So a big part of my work to implement this into our CI suite is that I didn't want to touch our existing CI infrastructure. So this was actually done completely in parallel to our existing CI setup, which was using our system packages. So the idea was that this could be done more or less piecewise, and by doing that, in practice, we also happen to have both done at the same time, which is really convenient. And we needed to test against that use case as well, especially for Aurora, for example. Aurora doesn't have Spack packages. Well, it does, but like it's a little complicated. So anyway, point being is that we need to test against the use case. So we do do it. Yeah.
So, very cool talk. Thank you. Okay. So thank you. Very cool talk. And just a quick comment for my question. I just really love you referring to MPICH as upstream, like you see yourself as a Linux distro maintainer first, never change. Okay, so I think back on slide 44, you don't have to go to it, but you talked about you're trying to generalize to a tool which templates specs for your CI to concretize and install. And I was visualizing this as you looking at your configure.ac script to build up the.
Yeah, so I think there's a few approaches that you could do for this. Yeah, so I think the way I did it mostly was I kind of did some opinion, because these automake configure flags are more or less standardized, right? You have with or without, right? You have enable or disable, right? And then so you can kind of use those in as general clues to generate equivalent Spack variants, right? So if I knew that, like for example, like with wrapper DL path, for example, I know that it's with as a prefix, right? Wrapper DL path is the value, right? I don't even need to explicitly write out a mapping. I can kind of just assume that this is what the mapping is going to be, and then if there's exceptions, then I have a special configuration file for the exceptions that I handle with an ad hoc basis.
Yeah, because I mean that's very nice. I know Spack has some like shortcuts within it to like.
I did think about too, like if I was to maybe make one there's one variant that does the entire configure flag set, or if I tried to use some environment variables and make the builds not pure. But in practice, I ended up doing this approach with the Spack specs because it's really nice also just to have the same interface. Like I can use the same Spack user interface and pull in packages like they were normally built, and it's very convenient to have in comparison.
Yeah, because depending on how much time your PI will allow, it'll be very nice if like the Spack, the Spack package create command, when it's creating like an AutoTools-based package, could maybe pull from that.
Yeah, exactly. So we were thinking about doing that, about templating out or essentially auto-generating Spack variants equivalent to, because it's just a Python module, right? So you can end up doing that. I think actually there was a talk last year that someone did something similar, and I was very interested in it at the time. This is more or less early experimental work, so we didn't have per se a lot of it was manually done that could be automated later down the road, but these were our ideas in our head. Exactly what you were thinking.